Hi, welcome to our project named Running Text on 7-segment display created in VHDL language. For implementation, we use the Nexus A750T board based on the latest RTX 7 field programmable gate array, so-called FPGA from the company Xilinx. As you can see here in this GIF, this was the main goal of the given task. Let's see how we got it to work. Here we have our top module. We could say that its purpose is to connect the sub-modules all together in one big piece. First things first, I would like to tell you more about the UART RX module, which you can see right here at the right bottom. This part of our program is responsible for our board's communication with computer via serial line. It basically uses a built-in bridge between the UART chip and the standard USB connector, which is used as a power supply but also as a programmer. To simplify the whole communication process, we can divide it to 3 phases. In the first phase comes the least significant start bit, defined as voltage drop from logical 1 to logical 0. If there is no communication on the bus, logical 1 is on. The next phase is receiving 8 bits of data coded to ASCII format from the computer. The communication is terminated by sending the most significant stop bit, which is indicated as a change from logical 0 to logical 1. In this picture, you can find UART or USB port under the number 25. And since this was not the main target of our project, let's move on. Now we are going to talk about the circular register module, which is right here. This module connects 8 simple piezo registers, and each of them is used for 1 bit weight. When we initialize this circuit, all registers are filled with zeros, except for the register at position 5. That one is filled with 1s because that's an ASCII code for white space which we need for the start of the next process. Resetting the module has a similar effect as initializing it from the very beginning. When we load wanted data to this register, we load them synchronously to all 8 registers, always to the same position. After this process, the stored data position index is incremented. For rotating the register, we use VHDL command ROR. This command rotates the register to right direction. That means that the data from position 0 will move on to the position 31 and so on. This obviously applies only for 32 characters register that we decided to use. If we load more than 32 characters, the registers start overwriting older data, as you can see here in the simulation. The next topic awaiting us is the clock enable module that can be seen here under the circular register. This module simply counts up the rising edges of clock signal. When we reach a certain number set by the generic constant, the circuit generates an impulse that is in the length of 1 clock. We use that in another circuits for short enabling function for 1 clock period too. That means we don't need any clock divider, we generate short pulses after a certain amount of clock periods. The module was already created in one of our lectures, so we basically just copied it and adjusted it. One of the most crucial parts of our project is the ASCII validator, which is here at the left top. This module simply checks the user input data, and if they're on our list of allowed characters in ASCII format, it transforms them into 7-segment signals and sends them to the register. The validator was created to recognize characters such as numbers, a dot, a comma, the question and exclamation marks, and white space. When it comes to letters, it only sends out the uppercase ones. So we made it possible for the module to receive the lowercase letters and convert them to uppercase letters. If the ASCII validator receives unknown data, nothing is sent to the register, as you can see here in the simulation. The biggest module in the top, our display driver, takes the input value, shifts all the previous ones to the left, and discards the leftmost one. This happens only when the enable signal is present. Then the input value is converted to 7-segment code and is displayed on the 7-segment display. Just like here, when no value is currently being received, it only multiplexes and updates all 8 digits. To sum it all up, all of this theory was quite good and thought through by us, but on the real hardware it didn't quite work. There were some problems with loading data via serial line. In order to fix it, we have tried many things, such as flipping bit order or adjusting, even removing some modules, but nothing worked. Since the main topic of our project was just a basic running text on 7-segment display, we decided to fill the data register with static data. However, for proper function, we only need serial data stream, meaning the module could be easily replaced with debugged module from another application. Thank you for your attention.